right, hey everybody, and welcome back to Adventures in Machine Learning. Today, we've got Francois Bertrand on the panel.
Hello.
I'm Ben Wilson, and our guests today are Elena and Emeli from Evidently AI.
Hi there.
When I went freelance, I was still only a few years into my development career. My first contract, I was paid $60 an hour. Due to feedback from my friends, I raised it to $120 an hour on the next contract. And due to the podcasts I was involved in and the screencasts I had made in the past, I started getting calls from people I'd never even heard of who wanted me to do development work for them because I had done that kind of work or talked about or demonstrated that kind of work in the videos and podcasts that I was making. Within a year, I was able to more than double my freelancing rates, and I had more work than I could handle. If you're thinking about freelancing or have a profitable but not busy or fulfilling freelance practice, let me show you how to do it in my Dev Heroes Accelerator. Dev Heroes aren't just people who devs admire, they're also people who deliver for clients who know, like, and trust them. Let me help you double your income and fill your slowdowns. You can learn more at devheroesaccelerator.com.
All right, so we asked you to come on to the podcast because you did something pretty cool a couple of months ago. And I got aware of it because of your involvement in the MLOps community. Last week's episode, we had Dimitrios on, and we were talking about what that community is like and how it brings people together that are doing cool stuff in this industry and in this space. And I noticed a couple of posts, Elena, that you had made, and you had answered some people's questions. And I was in the process of writing a chapter in the book about ML engineering on this topic. And then I see that you make a post. I'm like, whoa, somebody's actually open sourcing this that is going to potentially save me weeks of work anytime I need to implement this for a customer or need to give people advice on how to do this. So it was really interesting to see that. And then I checked out the code base and got really excited and started talking about it a bit. And we're finally here to talk on the podcast about what you've built. And if you could just sum it up for the listeners about what it was that you built initially and why you built it.
Let me maybe start with a bit of a background because the why comes a lot from our past experiences, both me and Emeli. We actually have been working in applied machine learning area for more than 7 years, working with different companies, helping them develop solutions that optimize particular business processes with machine learning, from retail, manufacturing, telecommunications, you name it. And we've seen a lot of things that can go right and wrong with machine learning projects. And we actually were lucky to see quite some of them go to production and be used for the first time. And there are so many problems that actually became apparent only after you put these models to good use, right? So when you want them to continue to deliver the business value that they intend to, that we saw that this is completely an unaddressed problem because it's fairly new. Not many companies having models in production, especially if you look at traditional enterprises. And there is not enough best practices yet in how you maintain these models for the long term. And we saw this as an opportunity and embarked to build this company and this open source project first that focuses on machine learning model monitoring and drift detection. And in a nutshell, right now, what we have is a Python library that helps you visualize the model performance and analyze it and evaluate it in production, detect things like data drift, model prediction drift, where the model is making errors, and so on. So this is like a high-level overview, and right now it is used by enterprise data scientists, like individual machine learning engineers, to solve their own problem. But we have big plans into turning it into a more comprehensive machine learning model monitoring platform.
And that's something that, as I've been watching the repo and Emeli's commits over the last couple of months, I've kind of seen that trajectory of like, whoa, they're making a service here. And they're integrating with all of these very popular open source frameworks of like, hey, you can make this as part of a DAG in Airflow and kick this off. So it's really exciting to see that. And I'm hearing buzz from others about that, which is really cool. So when we talk about problems in production and in people that are working in this field when they're new to it, and this is sort of a company that wants to do ML, they have a pretty good idea of a problem that they want to solve, and they've hired some data scientists or hired a consulting company to come in and build it. Most people are myopically focused on prod release as saying, hey, we're good to go. We have a model. It's doing predictions. We have it on a cron schedule, or it's doing real-time inference. But what is it about this drift that makes that not the case, where production release actually isn't the end of the story?
Well, let me comment there. In most cases, when you just start using your model into service, you want to make sure that everything works exactly as it worked on the historical data and you try to analyze model's performance. But together with the model performance, it's super important to make sure that the data that we use as an input for our model is still the same and still has same distribution and same properties. And data drift is a way how we can analyze the, let's say, similarity of data and compare data from the current period of time with the data from the period of time where we trained our model or made some experiments. In most cases, when we analyze data drift, we compare distributions. We use the statistical tests to compare distribution from historical data with the current data. And, well, there are many, many different ways how we can do it because, well, the input data are different. We can have categorical features, binary features, numerical features, and what's not. And there are a lot of different statistical tests that we can apply to compare distributions and see if there are some changes or everything is okay.
So if we're using something like that most data scientists are relatively familiar with, like a KS test, when we're looking at continuous distributions, and a naive implementation that somebody might do is say, I need to just say, hey, these are effectively exactly equivalent. Have you ever seen that in real world data where things are like, hey, I have an alpha of 0.01. And if it's outside of that range, I'm saying, oh, this is data drift has occurred. Or do you see more of boundaries that are set, saying, hey, we can accept a threshold here of changes before we alert on?
Well, for me, it's a bit tricky there because before we're actually calculating the statistical tests, we need at least to figure out what window sizes we use because, well, when we compare the smaller windows, sometimes it's easier to detect drift. But, well, okay, I will not say that again because it's really depends on the data. But anyway, it depends on the window size, right? And when it comes to model performance analysis, it's super important whether this numerical feature we are talking about is the key feature for the model or not. Because at some point we can build the model on top of a lot of like pretty big features and this model will still perform pretty well. Or vice versa, we can have features with different importance and some of them will be more important. And in most cases, I would say if I saw something like this, I would react this way, like let's stop everything and rebuild the model or dig deeper to figure out what has happened only if I know that this feature is super important. In most cases, I think it makes sense to analyze drift on like all features we have and see what percentage of feature are drifting and how much it affect the model.
That really reminds me of one of the first times that I attempted to build a system like this, like manually myself. I was under the wrong impression that like, hey, every feature is super important and I need to create statistical process control rules around every single feature. And this is like more than a decade ago, back when I really didn't know what I was doing. Now I just kind of don't know what I'm doing. And I had put all of these alerts and I said, oh, I need this threshold around these values. And if my distribution changes on all of these by just doing normalcy and equivalency tests and saying, oh, is this really a difference? I remember the model that I was evaluating had about 100 features, which was way too many for what that model was doing. And I had alarm fatigue after just 24 hours of turning the system on. Everything was alarming constantly because it was doing 24-hour windows. And I was panicking and coming in every morning and saying, oh, I got to retrain the model again today because features drifted. Oh, geez. And then I noticed that the performance of the model didn't change at all. Like ever, just retraining, adding another day of data. And then somebody was a little bit more experienced than me was like, hey, Ben, did you check what the importances are of the model? It's like, well, what do you mean? It's not a tree-based model. I can't get feature importances. I'm like, no, the coefficients to the linear model. Check what that value is. It's like, oh, it's 1e to the negative 16. And they're like, yeah, not important, man. But this other one, that one that's a very big number to that. Make sure that one's validated. So when we're talking about the features that are coming in and monitoring that's one aspect of drift that people care about or should be caring about. What about on the other side when we're running predictions and we want to make sure that we're not predicting something ridiculous over time?
From my point of view, the predictions are much much more important. So if I would see some trends or differences in distributions for models output, this would go an alarm. I mean, sometimes if, for example, we have models like linear model, which can, let's say, which extrapolate pretty well, and we see that there are some linear trends in our input data, and we expect, for example, the model's output to be higher because some important features are higher, and this is okay from the domain area point of view, then maybe it's okay. So we're seeing some trends in the input data, in the model's output, and we kind of agree with that. But in other cases where we do not expect model's output changing and we see some changes, that can be an early signal of some potential quality decrease because, well, when we do not expect such changes and we see that the model's output is changing, that probably we need to intervene and figure out what is happening. It's especially important when we have our ground truth with the delay and we cannot calculate the model performance right there. We need to wait while we get the ground truth, the real values, the true labels, right? And if we already start seeing that the model's output is changing, maybe it's time to take some actions or at least try to get the ground truth faster or maybe analyze some other proxy metrics that can help to figure out whether the change in output is something that we agree with or not.
Yeah, and that becomes super important for certain applications of ML. And the danger of not having that feedback for certain applications that people are trying to solve arises quite a bit depending on the application. So you think of something like, hey, we're trying to prevent or detect fraud, for instance, of transactions. We're a B2C company and customers are interfacing with us and buying products, having stuff shipped to us. And if you have a model that's trying to detect fraudulent activity, if you're not getting that feedback back to the prediction to block transactions fast enough, or even worst case scenario, you're not even looking at it at all and just assuming that, hey, this works fine. It becomes a big danger if people put faith in that model and in the data science team that's maintaining it or that built it. If all of a sudden 3 weeks later, people are like, oh, some hackers kind of penetration tested our approach here and they found out how to defeat the model. Why didn't you guys catch that? So when you get down to situations like that, having a tool like Evidently running on those predictions and creating that surrogate test, or you're saying, are we actually detecting fraud at the same rate that we were before? Because all things being equal, you would expect that even though that is sort of an illegal activity that's happening, that there's enough bad humans out there trying to do that stuff. You would expect some sort of baseline over time. And if all of a sudden the fraud predictions start trailing off, that can be an indication of, hey, maybe somebody adapted to what we're detecting here. So Evidently can do that, right? It's monitoring that rate of prediction and saying, hey, something has changed here.
It's probably one thing that you could look at, but when it comes to that degree of criticality of use cases, you can also look for outliers and like maybe add some additional guardrails on top of it. Because when you talk about drift detection, it's more like looking at the like overall trend. So like we need to wait till some critical mass of events accumulate, right, for the statistical test to react, depending on how it is set up. So for some use cases, you would probably need like even more thoroughness in how you look at them, like outlier detection and maybe setting up some, like human in the loop review if you fire like an alarm or like raise suspicion for one particular model decision. So it can even get even more comprehensive like than just drift detection, but indeed looking at the model inputs, looking at the trends in model outputs and statistical changes. This is what we are doing now. We will add some more stuff, and all this is hugely important. The more important the use case is, right? The more the cost of the error, the more the revenue the model generates, or the higher the potential risk if something goes off the rails.
Yeah, and I want to bring up for people listening, another potentially very interesting, at least from what I've seen at your stuff, is that for the people listening, a really good use for Evidently. I'd like you to maybe talk about how your Evidently is this great tool for monitoring performance versus the past, but you're really just comparing two models, right? Or one model on present data and past data. And you mentioned that it has also uses for if you're even before getting to production, how big of a use case is it to, let's say, compare between two models outright with the same data? Instead of just changing the data, you change the models, but on the same data. I'm figuring this could be really useful to compare two models and where they go right or wrong.
Indeed, the beauty of building an open source tool is like when you put it out there, the people start using it the way they like and the way they find it useful. And even though initially, like we were looking at this monitoring and drift analysis, like in a focus on model production use, right? Then it became apparent to us and also to our users that we basically built very beautiful visual reports, which help you to compare anything to anything. And it can be like comparing two different models between each other, also analyzing the model performance like on a test data, maybe some A/B test results. And a lot of our users say that they indeed use Evidently like this. And we welcome this highly. Probably like there are even maybe more users that are using it before production simply because more people are still in the pre-production phases of machine learning. But we welcome that highly too. And yeah, that was interesting kind of like user feedback that we got. I don't have the exact numbers, but the trend that we are like getting from our users is indeed there. Many people just like the reporting functionality too.
Yeah, because I was looking at it, I was like, oh, that's really cool, but I'm not really doing a whole lot of production, production stuff. So yeah, I thought that would be really cool just for the model. So that's great to see that people are using it that way.
I thought about one more like use case, and we're lucky to see that happening, which is more of an exchange between like data scientists and sometimes even the business counterparts. And this is something that me and Emeli experienced in our past life, right? So when you're working on some project and machine learning implementation, you have like more than one stakeholder, right? You have a data scientist, you have the business stakeholder who is engaged, and very often you need to communicate between the two and just basically explain things like, hey, the data doesn't look good, right? But when you want to communicate it, you want to show something like these are the distributions, that's how they changed, right? Can you please tell me like if this exact feature is it actually looking the way it should? In our past life, we worked a lot with manufacturing. And for example, there we had like a lot of sensor data, which have like completely particular drift patterns. The sensor is broken, like it still doesn't fire off an alarm. It still stays within the range, but it looks completely different in terms of pattern. So like collaborating on these things is very important. And when we were building the tool, we thought that like shareability and being able to export these reports and exchange them like between data scientists and someone else is very important. And we're glad that people are saying that they're using it this way. They're just basically getting these reports and they're sending them to someone else within the team, within the company, or external clients if this is more of a consulting user. So yeah, that's also interesting thing that we learned